Hello everyone, here is Mr. Bistawi. This is Chapter 6, Kinetics, our first lesson about the collision theory and rate of chemical reaction. Let's get started. In this first lesson, we have a number of objectives. The first objective is about the rate of chemical reaction, how we can define it based on understanding to it. Number 2, describe experimental methods for measuring the rate of various types of chemical reactions. 3, analyze numerical and graphical data from rate experiments. When we are considering a chemical reaction, we consider two main components, which are the reactants and the products. For that reason, when we would like to speak about the rate of a chemical reaction, we have to refer to reactants or products. Of course, when the reaction is proceeding, the reactants will be used up and the products will be formed. So the speed at which the reactants are used up or products are formed is considered to be the rate of the chemical reaction. We have different experiments to measure this rate, the rate of the chemical reaction. Also, based on the reactants and the products, the consumption of reactants and the formation of products. Consider the reaction between calcium carbonate and the hydrochloric acid. Here's the reaction, as you can see here, solid calcium carbonate with the HCl, hydrochloric acid. We have calcium chloride, carbon dioxide, H2O, water as a product. If we'd like to calculate or to check the rate of this reaction, we have to have a look on both reactants and products. We have here the reactants. Okay, solid and aqueous. And we have here in the products, we have gas. So we just have to think, how can I check the formation of the products, or how I can check the consumption of the reactants? We'll find that we have two ways to check the rate of the chemical reaction. The first way is measuring the rate at which carbon dioxide is produced. So now we are speaking about the products. Products will be formed. So we have to have a setup that could allow us to collect carbon dioxide and to be able to check its formation. Here's the setup that we can use. Here's calcium carbonate, hydrochloric acid, carbon dioxide. Of course, it has to be sealed so that the gas will not escape outside the system. Then we can collect this delivery tube. Here we can collect carbon dioxide. And of course, using this measuring cylinder, we will be able to know the amount of carbon dioxide that has been produced from the reaction between hydrochloric acid and calcium carbonate. Based on the amount per time, what's the volume that has been collected from the carbon dioxide per time, we will be able to calculate or to know the rate of the chemical reaction. As you can see here, here's the graph that represents the formation of the products. We have here some stations, or we have here some notes that has to be clarified. First of all, we are starting from zero. Why we're starting from zero? Because when we are starting in a chemical reaction, we have no products, we have only reactants. For that reason, we have here the products are starting from zero. Then we can observe that the beginning of the reaction is much faster than this part is steeper than this part. This part here is considered to be the initial, representing the initial rate, This very beginning part is representing the initial rate. And it, of course, is much steeper than the other part, because when we start mixing our reactants, the reaction is fast, then it has to slow down. until the reactants are used up and all the products are formed. Then we will find that the products had already reached to the maximum amount that could be produced from these types of reactants. The other experiment that we can carry out to check the rate of the chemical reaction is based on measuring the rate at which the mass decreases. Which mass will decrease, reactants or products? Of course, it will be reactants will decrease. What we can do, based, of course, on our reaction here, we can see that we have here hydrochloric acid, calcium carbonate, of course carbon dioxide will be produced. So we'll have here cotton wool to prevent any of these reactants from escaping, but of course it will allow the escape of carbon dioxide. So we will observe that if we started here with this certain mass, after a while we'll observe that this mass is decreasing. Why this mass is decreasing? Because of the carbon dioxide which is leaving the system. And we can see here this graph which is representing the change in mass with time. We already started from this number and it is going down, down, down until it is fixed. Sometimes we will not, one of you will tell me why we didn't reach to like a certain why you didn't reach to 0, because we still have here in our beaker, we still have our reactants. We still have our reactants, we still have some of our products are not escaping. For that reason, we'll never reach to 0. This mass difference is representing only the amount of carbon dioxide that escaped from the beaker when the reaction started until the all the carbon dioxide already escaped. And so we should understand that for any chemical reaction, we have reactants, we have products. We can check the rate of the chemical reaction based on the consumption or how the reactants will be used. So the speed at which the reactants are used up is representing the rate of the chemical reaction, or the speed at which the products are formed is representing also the rate of the reaction. Well, so to calculate the rate of the chemical reaction, we are supposed to check the change of concentration of reactants or products with time. So you can find here the units for the concentration and time, which is the concentration per second. You can see here the rate. The rate is calculated using reactants or products. The only difference is the reactants are negative. Why negative? Why am I including negative sign here? Because reactants are used up. So if we started with 10 reactants and by 1, so we have negative, the change is -9. So this negative sign is representing the how the reactants are used up per the change in time. Also, the products are, we should check the change concentration of products per change in time. We can also notice a very important thing, which is the square brackets. Square brackets are representing concentration. So if I'm putting here whatever HCl, so I mean the change in the concentration of HCl. I'm putting whatever the compound, whatever the molecule is between square brackets, so it means change in concentration. Why HCl is written like that is corrected, so HCl. We can observe here this graph, which is representing the data that we have here in this table. We can see from this graph that it is representing the change in reactants or products, we can see that this graph is increasing. Here there's something increasing, 0 till from 0 till we can say from 0 till 60, so something like that. So we can see that this is the products, because products are formed, products are getting formed, so we have more products are produced per time. And we have what's called initial rate. What's the initial rate? It is the rate in the beginning of the chemical reaction, and it could be measured through this tangent. Then we can check the slope, and we can of course calculate the initial rate. So the rate, here's the rate, change in volume per time. So where's the volume? We have started here from 0 because carbon dioxide is a product from the reaction. Then we ended by 60. Okay, so the change is 60. Then we have also the change in time, which is 90. Why did we say 90? Because after 90 we still have the same amount of carbon dioxide produced, so we have to stop at 90. So it's 60 over 90, so it is 0.67 centimeter cube over second or per second. This is calculating the rate using the change in volume per time. Initial rate through drawing the tangent here, drawing the tangent. After drawing the tangent, we can check the change, we can check the gradient, change in volume per time. Change in volume here, 64 over 30, so this is the initial rate. Most of the questions are always asking you in the test, how can you calculate the initial rate? You can calculate the initial rate by drawing the tangent starting from 0. Then after drawing the tangent, you can check the gradient or the slope, and you will be able to calculate the initial rate. Change in volume per time. Change in volume was the amount of volume that has been produced per time. Then you will be able to calculate the initial rate. We have said that we have for the chemical reaction, we have reactants and we have products. These are the two main components of any reaction. Of course, we have reactants and we have products. How we may observe the rate of the chemical reaction. We can observe it through change in the pH for acid-base reaction. If we are starting from if we have like neutralization reaction, we will have a change in the pH. If we have acids and bases, of course, we have change in the pH. So change in conductivity, change in mass or volume, change in color. These are the four things that will be used for us to observe the rate of the chemical reaction. We have here an example about the observing the rate of reaction using change in color, which is always about the iodine. We have here iodine. As you may know, iodine is always brown color. So when we have iodine, it is brown, and all other species that we have in our reaction or in our whatever the reaction we have are colorless, especially if we have like propanone. So we are just starting the reaction with propanone and iodine. Iodine is brown and all other species are colorless. The reaction mix, when we start the reaction mix fades from brown to colorless as iodine is used up in this reaction. So here, before mixing both reactants, we were having the brown color of iodine. Then when you start mixing the propanone with iodine, we will have iodopropanone, which is colorless, and of course the iodide ions are colorless. The decrease in the absorption of light can be measured using calorimeter. So we have here the source of light, we have here filter sample, and we can have here our detector, and we can observe here the change in the absorbance per time to check the change in color. The absorbance falls with the time as iodine is used up. Iodine is used up. And on the other curve, a calibration curve is used to convert the absorbance of iodine to a concentration. So we have here the absorbance and concentration, against concentration. It can be constructed by measuring the absorbance of several solutions of known iodine concentrations.